So shall we start?
I think it's sharp 7 and we should start. Yes.
Welcome all participants to the 10th Indian Epilepsy Society EEG workshop. We have previously, during the COVID times, made the workshop virtual. This enables more and more participants to come for the workshop and attend it, as well as, attend to their clinical schedules in the morning. I'm thankful to the president of the society, Professor Manmohan Mendiratha, for gracing the occasion as a chairperson. And as I wait for Dr. Sangeeta Rawat to also join as a chairperson. There are a few housekeeping announcements. I would request all the participants to please view the workshop, the entire workshop, on their laptops. This is because as we go along, there's a series of 22 sessions. As we go along, you will see EEG in details, and you may miss out on, waveforms, or a spike may appear as a sharp wave, or, on your mobile, because that's not digitally synchronized or calibrated to the EEG. So I request all of you to view the workshop on the laptop. In case there are any patient videos, as we may have in few of the sessions, no recording of the patient videos should be done. The other announcements are that as participants, we expect 80% or more participation for, getting a certificate of attendance from the society. So we have purposefully kept this workshop without any charges, but we expect you to attend 80% or more, and that we will know from your attendance sheet after each program. At the end of the workshop, we have a quiz, and of course there would be a marking of the quiz, and the top 3 scorers would get a complimentary waiver of registration for the Econ 2023 in Jaipur in July. I also request you all to put your questions in the chat boxes, and they will be taken up one by one after the session is over. With this few words of housekeeping, I request Professor Manmohan Mendiratha to give his welcome, and following which Professor Manmohan Mendiratha would be delivering a talk on the history of EEG. These are things which we don't often discuss, but they're so very important. And all of us know Professor Manmohan Mendiratha is the president of the Indian Epilepsy Society. And he was the professor and head of department, GB Pant Hospital, Department of Neurology, and is currently in BL Kapoor, Hospital in Delhi. He's one of the most eminent epileptologists our country has seen. He is also an ambassador for epilepsy, and he has mentored many of us to educational programs of the Indian Epilepsy Society. This will be followed by a talk by Dr. Sita Jayalakshmi, who is a very esteemed colleague at the Krishna Institute of Medical Sciences, Hyderabad, and has dedicated her life to patient care for difficult epilepsies as well as research. So with this few words, I hand over to Professor Manmohan Mendiratha.
Good evening, friends. At the outset, I like to extend a very happy, healthy, and bright 23 to all of you. At the outset, I must say that you must be very excited to participate in these EEG workshops. And we are also very encouraged by the response of yours. I have been told there are around 600 registrations. These days, there are so many webinars and attendance is very few. Chairperson and some participants, sometimes only 10, 20, 30, but we expect this to be very successful workshop. Dr. Manjari Tripathi, as Secretary General of Indian Epilepsy Society, has worked very hard. We had been in touch, and this had been an earlier annual affair, but because of COVID, we had to organize virtually. And the colleagues like Sangeeta Rawat, Sita Jayalakshmi, and other colleagues who will be delivering talks have been instrumental in putting their best efforts to make it successful. And I will be speaking on, I'll just share my slides. And I'll say, I'm sure most of you must be a member of Indian Epilepsy Society. If you plan, you are a neurologist, you will be practicing epilepsy, whether you are epileptologist or not. So I will request, and I'm sure Dr. Manjari will be very with this announcement, that all those who are not members should become member of Indian Epilepsy Society. And there are a lot of benefits and advantages of becoming a member. So it's a one-time life membership. It's not like international membership where annually you have to pay a few $100s. Here it's very, very nominal amount, and you are lifelong the member of the society. So I will just start my slides and try to finish, if not in 15 minutes, as early as possible. So the topic which I have been given is history and evolution of human EEG. I'll take you through this before Christ, after divine. So that's the way it has evolved. And this is my brief CV. As Dr. Manjari is now Secretary General, earlier I was the Secretary General, and we have done a lot of guidelines in epilepsy, like on phenobarbital, diphenylhydantoin, fosphenytoin, valproic acid, conventional anti-epileptic drugs. And now we are again trying to have revised guidelines because a lot of water has flown under bridge. There have been new kids on the block, and new kids are coming on the block. So there will be another guideline coming up. So I bring greetings from New Delhi. What I say is your eyes will see what your brain knows, right? So when EEG, if we don't know something, we may pass off as normal or overreading, like saying abnormal, a physiological variation, an eye movement, muscle artifacts, or some other activity may be passed off as pathological. So often it's, I will say, these are underdiagnosed or at times overdiagnosed entity through the EEG. The other important statement is Rome was not built in a day. So evolution of EEG has not been overnight. And let us go through it, how it has been. Hans Berger, father of EEG. All residents must remember he is labeled as father of EEG. We see in the electroencephalogram a concomitant phenomena of the continuous nerve process which takes place in the brain. Exactly as the electrocardiogram or electrical activity represents a concomitant phenomena of the contraction of the individual segments of the heart. So you all are aware of ECG, but ECG takes just few seconds, right? EEG has to be at least around half an hour. 20 minutes to 30 minutes is mandatory. And if you are short of that in recording and printing, it's not a good job. Now, introduction. Epilepsy has been known since antiquity, and the first description of it can be found in multiple cultures. Why I'm saying this? Because EEG by and large is used in epileptic disorders. Though there are other things like encephalopathies, CJD, and so many other conditions, or brain death. But this was including in the era of Mesopotamia, Akkadian, and ancient Babylonians, about 2000 years BC. As I said, BC, and then I will come to AD. Greeks, 4th BC. The basis of therapy in this area fell into 4 main categories: conventional, marginal, trepanation, and religious procedures. Religious procedures are still followed in number of areas, even in our country. Several centuries later, the generation of electricity marked the beginning of electroencephalography, starting in the medieval times with Gilbert, Galileo, and Willis. If you have to know about the history and evolution of EEG, one article everybody must read. This was published in Journal of Clinical Neurophysiology in 1993, American Electroencephalographic Society. So before Christ, let us have a look on before Christ, and not starting only with Hans Berger. We move from animal lab experiment to human neurophysiology lab. Now, Hippocrates, in the time of Hippocrates, he challenged the theory that epilepsy was a disease of the gods, providing an objective description of the disease that is not divine and not sacred. Has the same origin as other illnesses, begins during embryogenesis, may begin. This was thought, and has a worse prognosis for children compared to adults. He probably was talking of genetic epilepsy or inherited epilepsy. I will not read each and every word. Then come the discovery of the static electricity was first attributed. To record EEG, you need static electricity. Thales from Miletus, a pre-Socratic natural philosopher, mathematician, and astronomer of Greece, one of the 7 wise men of that time, around 640 BC, who generated friction using amber against silk or fur. Sometimes we rub against the cloth, we get the current-like sensation. So that is what he did long back. Then comes the Byzantine era. There was enough knowledge regarding epilepsy, and several methods of treatment were used. However, the diagnostic criteria and management were both empirical. Now, then comes these big people. In the early Byzantine late antiquity area, prevailed the views of Hippocrates, Galen, we know vein of Galen, Alexander of Tralles, Oribasius of Pergamon, Paulus of Egina. Without reading, even I may not remember all the names. Etius of Amida. So these were the people who made a lot of contribution towards the current EEG what we know. So I will come slowly one by one to the other. Before the EEG, these days were the grand days of descriptive neurology. But now descriptive neurology, especially in epilepsy, is supplemented with the EEG description. Now, Tissot. The description of an epileptic diathesis as opposed to an evident cause of epileptic seizure was elegantly put forth by Tissot. In 1861, again we know Reynolds so good, James Russell Reynolds of London published a seminal work, Epilepsy, which was a summary of years of careful observation and attempts at treatment before the use of bromide in 1857. First time used by gynecologists, especially for status epilepticus of eclampsia. Then Hewling Jackson, father of electrophysiology, is credited with the first electrical theory of human epilepsy in 1873. Then comes Robert Todd. We know of Todd palsy. He presented an electrical theory in 1849, thinking of the brain as having battery-like properties and buttressed by his own studies in rabbits. So now the animals experiment or lab experiments are being mentioned. The era of encephalography beginning. How did it begin? Starting in the 16th to 17th century, the scientists William Gilbert, Galileo, Thomas Willis, Circle of Willis, fame, investigated electricity of various substances. Now, before Hans Berger, there was another German physicist, engineer, and natural philosopher, Otto, developed the first electrostatic apparatus, a sulfur ball that rotated on a shaft to produce electrical fields for basic animal experiments. We cannot extrapolate all animal activities in the human beings. These have to be further proven, which were proven later. Now, an Italian physician who demonstrated what we now understand to be the electrical basis of nerve impulses. In 1780, he accidentally made frog muscle twitch by jolting them a spark from an electrostatic machine. It was observed in 1870 through galvanometer. Many of you know that hind limb extension in epilepsy to find out about effectiveness of anti-seizure medicine in focal epilepsy. So it is something like that. Then came Alessandro Volta. We know voltameter was an Italian who devised voltameter, and he invented the electrophorus, a device that once electrically charged by having been found to have current in that. So then comes an English scientist is credited with discovering electrical activities of the brain by recording electrical activity from the brains of the animal using a sensitive galvanometer. So galvanometer has come, now the recording. Noting fluctuation in activity during sleep and absence of activity following death, develop long-term EEG monitoring or video EEG, what we call these days. Now then comes Polish physiologist and pioneer of electroencephalography. In 1890, Cybulski carried out one of the first ever EEG recording of the cerebral cortex. He conducted pioneering research on the electroencephalographic waves. Then comes Vladimir. We all are aware about Ukraine war these days. He was a Ukrainian psychologist. In 1912, he ordered the first animal EEG of mammal, dog. Then will come Richard Caton, then will come Hans Berger. Now here comes Polish physiologist started studies on the electrical brain activity of animals. I'll not read again each and every line. Using this technique, Beck localized various centers in the brain of several animal species. Now clinical neurophysiology and human EEG. Now we are coming from animal lab, experimental lab to human neurophysiology lab. Now here come Hans Berger. German psychiatrist, he was not a neurologist, he was a psychiatrist, recorded the first human EEG in 1924. So you will have to remember this. Like we remember Parkinson 1912. For EEG 1924 in subjects with pre-existing skull defects. So if there is a skull defect, there will be high amplitude activity. He was the first to use the term electroencephalogram. So the term EEG was actually given by Hans Berger. He also discovered the alpha and delta wave. An alpha wave is also called Berger rhythm or Berger wave. He was the first to suggest that abnormalities in EEG reflected clinical disorders. Berger believed that the EEG is analogous to EKG. That's what I have read a statement that he made. He was also first to record an absence seizure activity. And we were talking, Dr. Manjari and me, in our time, there used to be a question on history. And if you get a question on history, then you also have to know the tragic end of a great man. He had a tragic end. So I leave it to you. You all explore what was that tragic event, and we'll take up in the next session. Now, Penfield, neurosurgeon in Canada. He was the first to conduct brain mapping. He worked with patients with epilepsy, and he stimulated parts of the motor cortex to find which brain regions they were associated. He was the one who developed the sensory and motor homunculus. Homunculus, we know, like body, leg inside, and then on the surface, and the face area as the largest representation. So, and the hand. So this was all by Penfield. And that was the center to reckon with in the field of neurosurgery. Now, Adrian and Matthews, this we have seen in our time later, also measured electrical activity at this scale. They also studied entrainment of brain waves with photopic or photic simulation and demonstrated changes to EEG. So Adrian and Matthew are like photogenic response, harmonic response, subharmonic response, or photoconvulsive response. Fisher and Lowenbach first demonstrated epileptiform spike. You can see here. We may find it very easy, but look at the number of years spent on this. Almost more than a century was spent, and then came spikes. Gibbs and Gibbs, very famous epileptologist, became a pioneer in the field of EEG while working at Harvard with Davis and Lennox. Lennox gastro syndrome, what we know, Lennox is here. The electroencephalograph was primitive in the early 1930s, having only one channel. Now we talk of 16 channels, 32 channels, 128 channels. So this is all possible. And with digitization, which I'm sure Dr. Sita will be speaking, I am not covering those. In 1935, Gibbs asked Albert Grass to build a 3-channel EEG. When I joined as a resident in GB Pant Hospital in 1983, I saw a huge machine occupying almost half of the room, like earlier big computer had. And that was a pen deflection EEG. And we know at that time how calibration was important. That again, Dr. Sita will be discussing. The Gibbs published the book Atlas of Electroencephalography in 1941. So 1924, Hansberger, and Gibbs Atlas of EEG in 1941 with a second edition in 1951. I think I'll try to finish in another 2-3 minutes. Now this author mentioned named delta and theta waves. Earlier the alpha and gamma waves, which were described by Hansberger, and delta and theta waves. And then developed the set standard of electrode placement known as, then came 10-20 system, or the what we call double banana, or international 10-20 system. This measurement system is used today as a means of identifying specific brain regions. Many times in the exam when I have gone as examiner, I've asked the resident to mark 10-20 system on the skull and put the electrodes. So when you are in the lab, you must practice. Don't leave it only to the technician, because it's our duty to know this, that what is 10-20 system, how electrodes are placed, what is 10, what is 20, 10, 20, 20, 20, 20, then 10, right? 4 times 20, 2 times 10 makes 100. So every row will make it 100. During the 1930s, Davis participated in the development of electroencephalography and was the first person in the United States to have his brain wave scanned by an EEG device himself. Same you must have heard of Yun Kimura, who is so well known in electrophysiology. He will pick up the electrode, put on his median nerve, and demonstrate how the carpal tunnel syndrome looks like. He will also demonstrate blink reflex by putting the electrode on the supraorbital nerve. Now this American young electrical engineer in 1935 built a 3-channel EEG. First was 1-channel EEG at the Harvard Medical School. After his design, the EEG could be recorded on rolls of paper using ink and pen writer, which was analog machines, I was talking about Grass machine at that time. These spike and waves were described. Earlier we have seen spikes shortly by the American group of EEG pioneers, Davis and Gibbs, Lennox and Jesper. In 1936, Gibbs and Jesper described focal interictal spikes. These are some of the views of at that time. You can see how big is the machine. Look at this here. How big is the machine? Almost occupying so much space here, half of the room. Now, Eugene used EEG to study sleep. Then came sleep studies. Normal REM sleep. An American neurophysiologist, along with his father, described rapid eye movements, REM. He made the discovery after hours spent studying the eyelids of sleeping subjects. Now, Canadian neuroscientist He observed sharp waves in 1969. So first was spike and wave, before were normal, then REM, and now comes sharp waves. Sharp waves were described after spike and wave. He also showed that in the waking rat, hippocampal EEG is dominated by theta oscillation. For this, he gave a new term, rhythmic slow activity, or RSA. So theta oscillations, we know that can happen in certain types in the temporal lobe. So American-British neuroscientists investigated sharp waves in more detail in 1978 while studying the spatial memory of rats. Now, coming very close, an electroencephalograph system manufactured by Beckman instrument was used to monitor the brain waves of astronauts on the flight. Till now, we were talking on the ground. First, we talk of animal labs, then human neurophysiology lab, then comes in the astronauts and was used by NASA. Conclusions. EEG technology has significantly developed since its early creation by Hans Berger in human. The demise of EEG, though often predicted, seems once again far in the future. People thought it is of hardly any value. This simple yet revolutionary method of studying brain function will likely continue to benefit from advances in technology. Now we are talking of machine learning, artificial intelligence that are yet to come. Its theoretical limits may not have yet been reached. New technology is currently trying to implement EEG into more accurate, non-invasive medical tools. Now let us recapitulate. Now, 1875, Richard Caton records brain potential from cortex of dogs. Marcox discovers evoked potentials. Hans Berger records electrical activity from skull in 1929. He first described 1924, but recorded in 1929. Grey-Walter finds abnormal activity with tumors. Toposcope imaging of electrical brain activity, or earlier in our time, we also had brain mapping or brain atlas. And color brain mapping quantitative EEG we have seen in our lab also on a big equipment. And now, good things, as I said, Rome was not built in a day. Good things, good results take time to come up. All it requires is patience and effort. Thank you so much for the very kind attention. I hand over the mic to Dr. Manjari.
Thank you, sir. And without history, we would not know the efforts put in to documenting the brain activity. And obviously, if one knows the history, one can develop better systems. Probably many of the youngsters who are attending today may work on such systems. I thank you once again. I request Dr. Sita Jayalakshmi to now give a very important talk on anatomy of the EEG system and the physics, and how it is important, because unless we know this, we will not be able to get good recordings from the EEG system. And this is often a neglected part of learning, because one gets so busy trying to see the waveforms that they don't remember, or they don't even identify the filter settings, which may give erroneous interpretations. Dr. Sita is now shared her slides. Dr. Sita?
Yeah. Thank you, Manjari. So can you see my slides? I have already shared.
Yes, your slides are visible.
Yeah. Okay. And you can hear me well. Yeah.
Yes.
Yeah. So thank you. I thank Dr. Mehendi Ratta and Dr. Manjari Tripathi for giving me this opportunity to be part of this very important teaching course on EEG. And today we will be discussing mostly about the technical aspects of the EEG recording. And we already heard a very important talk on the history of EEG, the amount of hard work which went over almost a century to have our comfortable digital EEG recordings today. And so I'll be briefly discussing about the physiological basis of EEG. How do we place the electrodes? What is the importance of filters, amplifiers? Why one should know about the sampling rate and resolution of the EEG? And how do you really arrange the montages to identify good recordings? So as we already heard, the evolution of the EEG, when you see in the time of Berger in 1929, the recordings are they're not very clear with lot of artifacts, and the recording system used to be very big, and the electrodes used were also needle electrodes at that time. But over the years, we are using microprocessor based EEG machines, and then digitized video EEG machines, which are available and which are very comfortable, where we can mobilize these units even to the bedside of the patient, into the ICUs, and we record. But still, there are a lot of artifacts, and it's very important that unless the neurologist knows, you cannot supervise your technologists to do a good quality recording so that the output generated and the reporting is good. So if you look at the EEG mechanics, there are so many advances which happened over the years in the electronics and the complex electric circuitry for the amplifiers. And hence, initially it was a 2-channel EEG. Now we do up to almost 256-channel EEGs, especially when we are doing the stereo EEG recordings. And even 512-channel recordings are also available. But nowadays we use anywhere between 8 to 32 channel, mostly 32 channel EEG recordings. And in polysomnography, we use 8 electrodes, which are related to the EEG recording. And if you look at the fundamental principles of EEG machine, it is a high input impedance machine. These are the important qualities. Whenever somebody buys, we should look at these parameters also. There should be differential amplification. The machine should have a good CMRR. We'll come to that. And there are multiple channels to record simultaneously from different scalp areas. And there should be, because there is a lot of data, especially when we are viewing the video, you should know how to use the storage, and proper output data should be there. So the EEG, how is the EEG generated? The brain generates the electrical activity normally, which is enough to power a flashlight. And EEG is nothing but the graphical description of the cortical electrical activity over a time, which is a dynamic process. And we are recording it from the surface of the scalp. There is high temporal resolution with the EEG, but there is a poor spatial resolution of the cortical disorders. That means we cannot record from the depths like hippocampus or from the cingulate gyrus. But however, EEG is a very important neurophysiological study for the diagnosis, prognosis, and the treatment of epilepsy. So if you look at the EEG, this is, for example, an electrode placed on the surface of the scalp. So what are we trying to record in this? So there are electrical potentials which are generated, so many underneath the electrodes. So from where are they coming from? The most important 3 potentials are the resting membrane potential of the neuron, which is mediated with a sodium-potassium pump, and it is mostly intracellularly negative. In addition, we do have the postsynaptic potentials, which are either the excitatory postsynaptic potentials or the inhibitory postsynaptic potentials, which are usually summated when we are recording the EEG. In addition, there is an action potential coming from the neurons, which is brief, larger in amplitude, which has an all or none phenomena. But however, what are we recording? The main generator of EEG fields is nothing but the summation of the excitatory and the inhibitory postsynaptic potentials, which are coming from the pyramidal neurons. That is the main one which you are recording, not the other potentials. So if you look at the EEG, in this EEG, normally how is the EEG recorded? There is single electrode on that. But what is it recording? It is nothing but it is the summation of the activity of many of the neurons, which should be detected on the EEG. And they should fire synchronously. If you see above, during the time when there is no synchronous firing, the EEG looks like that. And in the below, whenever there is synchronous firing, the EEG looks very clear. So it's important that the EEG is recorded only when there is a synchronous firing, which occurs during the epileptiform discharges. So the physiological basis of EEG is that it is the summated electrical dipoles generated by synchronously activated, and this is very important, vertically oriented dipoles, which are coming from the pyramidal neurons of the layer 3rd, 5th, as well as the 6th. Then coming to the electrical basis of the EEG, the surface EEG records potential difference between 2 points. It's not the potential, but it is the potential difference between the 2 points, that is between the 2 electrodes to say precisely, and which gets amplified by the machine. And these epileptic spikes are always surface negative because of the depolarization of the superficial lamina of the surface of the brain. And if you look at these dipoles can be obliquely oriented or horizontally oriented, but most of the dipoles are radially or obliquely oriented rather than horizontal or tangential dipoles, which occur specifically in certain conditions like benign Rolandic epilepsy. So how is the EEG rhythm generated? The EEG rhythm is generated once the EEG rhythm is generated from the pyramidal neurons. These are modulated by the subcortical structures, because of which we get either a spindle rhythm or a delta wave or alpha wave. The spindles are mainly because of the thalamocortical and thalamoreticular cellular networks. So this occurs especially during the sleep. Whereas the delta waves is generated by the cortical cells and it is transmitted to the RE cells. And then the alpha wave is generated by either the thalamic pacemaker or the occipital cortex. The most important is the thalamic pacemaker sometimes works, but however, the occipital cortex is supposed to be now known as the most important generator of the alpha waves. That is why what you record the alpha waves in the posterior cortex. Then it's important to understand that the solid angle theory says that only when a cortical region subtends a large solid angle for an electrode, the electrode records the potential which is generated by it. So the electrode should be subtended at a particular angle for the electrical activity to be generated. Then after this, what are the types of recording? Previously, we used to have analog recordings. Now we do have digital recordings, which made our life very easy. And we can use these machines even for long-term recording, where it varies from 1 hour to few days to almost 7 to 10 days based on the indication. This is the digital machine where you can see this is the monitor and this is the CPU and this is the junction box, and also which is electrodes are connected to the brain, and this is the photic stimulator which is attached to the same portion. And the monitor, if you look at, this is the very important part, which is the head box, where you can put the electrodes which are numbered very conveniently. So whatever the electrode is, it can go into that slot. And nowadays, this is the amplifier which amplifies the EEG signal. And whenever we are recording the EEG, one should know that the EEG should be conducted in a well-controlled environment. We should avoid having too much of traffic into the EEG labs. And there should be accurate placement of the electrodes. We'll come to that. And there should be proper understanding of the examination procedure by the patient as well as the technologist. And establishing a good rapport is important. And the technologist who is recording should have good knowledge of the artifacts. And they should make every effort to minimize the artifacts with observation and recording of the subject's condition to differentiate brain waves from the artifacts. Sometimes we get confused and the labeling by the technologists will help us in this. So always the EEG recording should be done in a quiet place with little machine vibrations. Humidity should be low, so always AC should be on. Low source of electrical noise. It should be away from the large AC units of the hospitals. It should not be close to any MRI or X-ray machine. And the examination is best conducted in a shielded room if possible. There should be an observation window for the technologist to see or monitor the camera. So if you see, this is just to summarize the EEG system, which goes to the junction box. And after that, the amplifier contains something called a differential amplifier, after which the EEG signal goes through a low frequency filter and a high frequency filter. So we'll come to the details of this. So all this one should be aware of. And whenever we are using the electrodes are made up of usually silver chloride, which usually are not polarized. So we can use a disc electrode, needle electrode, pad electrode. Most of the time we are using a cup electrode. And The electrode application also is very important. So because always we should measure the contact resistance that once we apply the electrodes, and when the patient moves vigorously or with prolonged monitoring, most of the time we use a crepe bandage around the head so that the electrodes do not come out. So the most important thing all of us should know is about how do we apply the electrodes. After that, we'll look into the other settings of the machine. So this electrode setting 1020 system was given in 1958 so that people from across the world can understand the abnormalities in the EEG just looking at the report, where the electrodes are placed at 10% or 20% of the distances between specified anatomical landmarks. So we use usually 21 electrodes, and we should know that all the odd number electrodes are on the left side and the even number electrodes on the right side. So for even if you look at the numbers, F indicates frontal. Again, F7 is usually anterior temporal, F3 again frontal, T3 is temporal, C3 is central, P3 is parietal, and OA is occipital. T5 is posterior temporal. So we should know where we are putting the electrodes. So similarly, the right side, you have all the even numbers. So what are the landmarks we are using when applying this? We should know one is Nasion, which is the indentation between the forehead and the nose. Inion is the occipital prominence. And in addition, we should know the preauricular points, which are indentations just above the cartilage, which covers the external ear opening. So this is just to show, this is the Nasion, this is the Inion, and this is the preauricular point. So now how do we apply these electrodes? The electrode site has logical alphabetical abbreviation which identifies the cortical area. And as I already mentioned, even that is all the even numbers are on the right side and odd numbers are on the left side. So now how do you place the electrodes? First, placing the electrodes in the anteroposterior plane. So from the Nasion to Inion, you draw a long line. Especially when somebody is doing the first EEG, you should do methodically by really using a tape. Once we get used to doing many, then one can go approximately. So the first 10% from Nasion will be FP. That is the frontopolar electrodes, FPZ. And similarly, posteriorly, the first 10% will become midline, that is OZ. The remaining area will be divided at 20% from the from FP to 20% is FZ. Everything is divided at 20% of the length. And you have CZ, PZ. And then you do a lateral measurement from the preauricular point to another. The initial is 10%, followed by the rest is 20%. So here you get T4, C4, and again C3 and T3. That is on the right and the left side. The other one is the circumferential measurement, where you go all around. And again, from FP to the right, 10% is FP1, to the left, 10% is FP2. After that, everything is 20%, and we get F7, F8, T3, T4, T5, T6, O1, and O2. So like this, we mark all the positions and then put your electrodes. In addition, you have the anterior-posterior measurements taken from the FP1 to get the F3, C3, P3, O1, all this is 20%. Similarly, on the opposite side, you get the FP2, F4, C4, P4, and O2. And finally, there is an anterior coronal measurement and a posterior coronal measurement. Both are of 20%. And you get the electrodes of F4, F8, F3, F7 anteriorly, P3, T5, P4, T6 posteriorly. And there is something called 10-10 system, which most of the time we do not use, where all the electrodes are placed at 10% instead of initial 10% followed by 20%. So once the electrodes are placed on the skull, we should know about the input section of the head box. The electrodes are plugged into the input section. The sockets corresponding to each electrode site is usually labeled and arranged, and the socket contains the numbers. So it's easy to identify. F3 will go into F3, PZ will go into PZ. It contains buffer amplifier or preamplifier to prevent interference from the external noise. So this is a preamplifier, so which connects to the PC, and you have this is very handheld and you can carry anywhere you want carefully. And after this, we should know what is impedance and resistance of the machine. Actually, both may sound synonymous, but impedance is measured using the alternating current, whereas resistance is the opposition to direct current flow, which usually gives the break in the electrical continuity. And normally we measure impedance once we connect all the electrodes. And how do you really check this? So a machine automatically gives you the impedance. If you see here, automatically once you connected the electrodes and switch on the impedance section of the machine, you can see whatever is in green, the impedance is good. If something is in red, the impedance is poor. Then again, you have to clean that area and also see that there is no dirt or sweat, and then you adjust it. And impedance should be between 100 to 5000 ohms. And this is everything is red here. That suggests that the impedance is not not between 100 to 5000. Normally, low impedance occurs whenever you apply a lot of jelly or when there is lot of sweat or the two electrodes are in contact with each other. No two electrodes should touch each other. Very high impedance occurs whenever there is a bad mechanical or electrical contact. Nowadays, we do have an amplifier with built-in head box. So here, this box contains both the junction box where you put all the electrodes as well as the amplifier. The next important thing is when you look at a EEG, when you are recording, you look at the channels to display, the time base, the montage, the sensitivity of the machine, and also there is something called the notch filter. So why do you need to have all this? There is a high cut filter and again a low cut filter. So we'll come to the details of this. So first, what is the role of amplifiers in the EEG machine? Normally, when the EEG is generated, if you see, it has a very low amplitude, which is 1000 times less than that of the ECG voltage. And so if you look at, this is the electrode 1 and electrode 2, the difference between this is becomes the output which manifests the EEG. So what do the amplifiers do? They do differential amplification. That is, that potential difference between input 1 and input 2, which comes out, will be amplified 1000 times by the amplifier in the EEG machine. So the each amplifier will have two important features. The first one is the common mode rejection ratio. So we will come to the details of this. So the EEG signal is measured as the difference in the voltage between two electrodes. For example, this is input 1 and this is input 2. So the difference between input 1 and input 2 becomes the output during the EEG. And similarly, if you see here, the input 1 is minus 40 minus input 2, which is plus 40. So it will become minus 40 will become minus 80. This is the deflection, which is upwards. The details of this will be discussed in some other class where the localization, how do you localize the EEG, will be discussed. Then coming to the common mode rejection ratio, that is what is this? So it is nothing but the effectiveness with which this differential amplification occurs and how the machine or amplifier discriminates between the in-phase and the out-of-phase signals presented in two input leads. So this is very important when somebody is taking the EEG machine. It's called CMRR. It should be either 80, it should be at least 80 decibels. Nowadays, we get machines which are more than 100 decibels. So the common mode rejection ratio of a digital EEG is usually more than 105. So it is the ability to differentiate the discriminate between in-phase and out-of-phase signals. Then after this, we come to the filters. So why do you have filters in the EEG machine? Normally, if you look at when you're recording the EEG signal, it is so clean and beautiful. But normally the EEG signal is a mixture of so many frequencies, not only from the brain, but lot of noise coming from around. That is, it can be coming from the biologically from the body of the patient or coming from the surrounding machines. The frequencies of the noise may overlap with the EEG frequencies, and hence the filters will help us to identify. Normally, the EEG signal is, the frequency is between low frequency. Why do you have a high frequency and a low frequency filter? So usually the EEG signal is below 70 Hertz and above 1 Hertz. So the high frequency filter is also known as low pass filter, and the low frequency filter is known as high pass filter. In addition, we use something called the notch filter. So let us come to this. First is the high frequency filter. The high frequency filter, usually we keep it around 70. Ideally, we should record at 70 hertz only, even if you are not getting a very smooth EEG. So it is the amplitude of the signal at a cutoff frequency, which is reduced by 20 to 30%. If you see, this is the recording at 70 hertz. This is not a good recording. So you need to really work on your placements, the impedance and the resistance. And if you change from to 15 hertz to have a good recording, that's what most of the time we get when we get the reference from outside. You see the EEG recording so smooth, which is not at all good. So we should never do that. And we should always record as far as possible at 70 hertz. So this is an EEG recording, which you can see is being done at 70 hertz. We are seeing some noise at the P4 electrode, because here the common electrode is P4. But however, we are seeing the spikes coming from the FP2, F8, F8, T2, T2, T4. And if you change it to 35 hertz, you can actually, the noise is gone. And most of the time you print this and give the, at 15 hertz, it becomes more smooth. You look at the morphology of the spike, what is happening. At 70 hertz, you can see the spike morphology very well. At 35 hertz, it's reasonably okay. And if you see at 15 hertz, the spike has become very smooth and something like a sharp wave. So the morphology of the important epileptiform discharges changes when you try to make the EEG smooth. So we should not do that. The second one is the low frequency filter. The low frequency filter is important to eliminate the direct current potentials, especially the sweat artifacts. So the low frequency filter is also known as the high pass filter. So here it's important to know what is the relation between time constant and low frequency filter in the EEG machine. Both are inversely proportional. So the time constant is inversely proportional to the frequency cutoff of low frequency filter. Normally, we keep around 1, the low frequency filter, with a time constant of 0.1. What is time constant? It is the time taken for a signal to decay from 100% to 1/3. That is 37%. So normally, if you keep, this is how you see the with the time constant, this is the wave of the EEG. But when you make it at 5, you see this, the morphology totally changes, and this is called over damping or under damping. So this is about the low cut filter of 0.01. You see, keep looking at the artifact as well as the spike morphology. And again at 0.1, 0.3, 0.5, 1.6, which is normally kept, and again at the 5. So both high frequency, low frequency filters, one should be careful when you are keeping it. Then the next one is filter is the notch filter. Why are we using the notch filter? Normally we get lot of noise coming from the electrical power lines. So the notch filter will cut off 50 hertz frequency, which is in India, and 60 hertz frequency from the USA. Actually, this is what is in the power lines. So whenever there is a noise, normally notch filter should be off only. But whenever you are getting lot of noise, especially if there is power lines close to the lab, then the notch filter has to be on. And this is just to show that when the notch filter is off, you can see that there is a lot of noise coming. Immediately we change it to the notch filter is on, then you can see the noise is gone. So this is how it occurs. So once we know that the amplifier, which has a high frequency filter, low frequency filter, as well as the notch filter, then how the display of the, so now we understood how we place the electrodes on the surface and how they come onto the junction box and then to the amplifier. And after that, how is it displayed onto the surface of the monitor? Normally, in analog unit, it was always a pen and paper, but nowadays we do not have it. So coming to the digital unit, in the digital unit, normally, how is the recording comes as nicely the alpha, beta, delta waves. Digital unit has something called the A to D converter. And in addition, there is a VGA display. So the digital EEG how normally the EEG which is coming from the brain is a discontinuous data, which is sampled by the machine, and this A to D card will convert that into a smooth wave and which is displayed. But to identify, to get this properly, we need two important things in the in the EEG machine. That is, the sampling rate of the EEG machine is important, and the voltage resolution is also important. So as I already said, this is the head box, and these are the amplifiers, and this is the A to D converter, which is already part of the CPU, which is displayed onto the screen of the computer. So normally the computer processes the data in discrete units or values, and this transformation of the continuous non-discrete EEG signal into a discontinuous or discrete data occurs for the display of the EEG. This is just to show the same thing during the analog to digital conversion. Normally, an analog machine with the pen will give a graph like this. But in a digital machine, all the data is in the form of so many dots. So it's very important that this dot should be sampled at every point throughout to get a proper recording. Otherwise, the recording gets affected. So the sampling rate is very important, and sampling frequency is important. Sampling rate is the rate at which the sample of the analog signal is taken in order to convert to digital form, whereas sampling frequency is the number of these measurements taken every second. So the sampling rate should be always high, and if you see the sampling rate is very low, the lowest graph, it is at 5 samples per second. You can see the graph is very poor. Whenever it is 200 samples per second, we can see the real time recording of the EEG activity as well as the slow wave activity, and hence the sampling rate should be high. Again, similarly, the more the sampling rate, the better the waveform. So normally, if there is undersampling, that is, if the sampling rate is very low, there is something called aliasing effect which occurs, which produces a lower frequency wave which does not exist in the original recording. So here, all the EEG machines use something called the Nyquist principle, which says that the sampling rate must be at least twice the fastest frequency of the signal. So similarly, if there is oversampling, the sharp wave will look like a spike, and if it is undersampling, the spike will look like a sharp wave. So we should be very clear that the sampling rate should be normal, it should be twice that of the highest frequency of the signal. But however, nowadays with increasing the sampling rate of more than 400 hertz, it occupies increased disk space, and hence there is a problem in again saving the data also. This is just to show when the sampling rate is low, how the EEG looks, and when the sampling rate is normal, this is the real EEG seen in the lower graph. So finally, the American EEG Society guidelines has suggested that for an EEG to be recorded at 70 hertz frequency, the sampling rate should be 3 times that of the highest frequency. So it should be around 210 hertz. But in most of the machines, what we get digitally nowadays, the sampling rate is around 256 hertz, which is reasonably good. Because the highest frequency we are recording is 70 hertz. But nowadays with SEEG recordings, we are using very high, almost even up to 1000 hertz. Then the resolution of the monitor is also important. It should be around 12 to 16 bits to avoid blocking of paroxysmally high amplitude signals. Then coming to so once we know all this, how the signals are coming, then you started recording on the digital machine. And whenever we start recording, most important is calibration. Calibration has 2 parts. One is mechanical calibration, second is biocalibration. So the mechanical calibration is normally done by all the technologies before starting by giving a 15 microvolt signal from the machine, which will produce a pen deflection of around 7 millimeters. This is mainly to make sure that in the analog machine, we used to make sure that all the pens are aligned properly, whereas in a digital machine, we look at the symmetry of the deflections. it is recommended that a second calibration should be performed even at the end of the EEG recording to make sure that during that 40 minutes of recording, the alignment is still maintained. So this is an example of a mechanical calibration in an analog machine, where you can see that you give this, this 50 microvolt signal so that the pen deflection is around 7 millivolts, and all the pen should be deflected equally and all the electrodes should react in a similar way. And if there is, this can, if the pens are not aligned properly, one can get something called under damping or over damping. This is an example of lower one is an example of under damping. The upper one is an example of over damping. But with the digital machines, the life is very smooth, and most of the time, because here there is no pen involved which is touching the paper, most of the time when we check the calibration, it is very nicely aligned, and this is the mechanical calibration what we see in a digital machine. Again, you see this in the, when you give 50 hertz current, then you can see this. This is the what you receive during the mechanical calibration. The next step is the biocalibration. In addition to mechanical calibration, biocalibration is also essential to ensure that all the amplifiers are responding equally and correctly to a variety of frequencies and not just to the current signal. So it means here the frequencies will be varying across the entire brain. This is usually done by using a frontopolar and an occipital electrode of opposite side. Both are connected to all the channels to get an identical input. This is the biocalibration of an analog machine, and this is the biocalibration of a digital machine. If you can see here, FP2 is connected to O2, and then most important is these are connected to all the channels to get identical output. This is the biocalibration. And sensitivity and gain we use on a day-to-day basis, where we adjust the sensitivity based on the voltage of the machine. And we can see if the voltage is of the amplitude is very high, we can adjust from 7 to 15 to 20 microvolts so that we will be able to look at the morphology of the wave well. The next one is paper speed. Normally, the paper speed is usually 30 millimeters per second, but paper speed can be reduced or increased nowadays to identify the changes. For example, at 15 millimeters, normally 30 millimeters per second is the common one. We make it 60 millimeters per second whenever you want to, where it becomes slow and you identify the ictal onsets, whereas you make it 15, especially when you want to see the discharges very closely, especially for periodic discharges of SSP and all, you adjust the paper speed so that you get the entire graph very carefully. So this is just to show at a paper speed of 30 millimeters, the 30 per second, you can see now there is some asymmetry just in front of the generalized discharges. That is on the right side, the discharges are starting early. When you make it 60, we can nicely make sure that definitely it is coming from the right side. So by adjusting, we can always make sure identify the mild early asymmetries pre or post ictally. So to summarize the recording, one should have the checklist before recording with a sensitivity of 7. Normally sensitivity is around 7, which can be adjusted, but most important are high frequency filter at 70 hertz, low frequency filter of 1.6 hertz, or the time constant of 0.1. Calibration voltage should be 50 microvolts, paper speed at 30 millimeters per second, and the AC filter should be always kept off. And one should make sure that the skin is prepared carefully to lower the resistance. One should check the electrode impedance, which should always be less than 10 kilo ohms. Unequal electrode resistance should be avoided. Apply a calibration signal followed by mechanical, followed by biocalibration signal. If both are fine, then start recording. And if required, use the additional electrodes. Always put an ECG electrode. EOG electroculography is very important, especially when we are doing sleep recordings and polysomnography. EMG also based on the indication, and respiratory monitoring in case of polysomnographies. So once we started recording, while recording also, we should have the information about the montages and derivations of the EEG. Derivation is nothing but the manner in which the electrodes are connected to the input. Montage is particular pattern of electrodes and the connections. We have referential montage, bipolar montage, common average montage. This is a longitudinal bipolar montage or so-called banana montage, which all of us use very regularly. The next one is referential montage, where one electrode, which is referential, usually either A1 or A2, connected to all the other electrode inputs. So this is an example of referential montage, where everything is connected to either A1 on the left side or A2 on the right side with all the electrodes. And in this, the localization is by the amplitude. Wherever it is maximum, we say that is the maximum surface negativity, which is closest to that electrode, is possibly the closest to the electrode is the epileptiform activity is coming from there. So this is just to show, if here it is showing from the F4, all are connected to A2 here. Then the choice of reference electrode can be either A1 or A2 mostly, but we avoid this in temporal lobe epilepsies. Similarly, we avoid CZ in sleep-related epilepsies. These electrodes can be organized into longitudinal, transverse, or circular montages. This is an example. Mostly the double banana montage, otherwise called the longitudinal montage, where they are connected longitudinally. Whereas otherwise, the other one is otherwise known as anteroposterior montage. We do have the transverse montage, where you connect all electrodes transversely, and circular montage can be on the clockwise or in the anti-clockwise. Automatically, these are now, we program all this within the machines, and the moment you go to that montage, automatically the EEG also changes. Why this is important is, okay, I'll come to that. Referential montage is where A1 is connected to all the left side electrodes and A2 is connected to all the right sided electrodes. This is just to show an example. This is a longitudinal bipolar montage. And then in a transverse montage, again, you see the spikes. So here again, this is clockwise connection and anti-clockwise connection. So this is an example of circular montage, where you are seeing this is the bipolar montage, where you are seeing the posterior spikes. By connecting them circularly, you identify that in between the occipital leads is the maximum or phase reversal happening, suggesting that possibly the focus is in between O1 and O2. The advantage with so many montages is good localization is possible whenever there is a phase reversal which occurs at same electrode in two montages which are running at right angles to each other. For example, you identify a phase reversal both in a longitudinal as well as the transverse montage in the same electrode, then you are 100% sure that the epileptiform activity is close to that electrode. Important another montage is the common average reference montage, where it displays the potential difference between each electrode and average of that entire array. For example, if you have a longitudinal electrode, FZ versus the average of entire longitudinal array will be calculated. So this is an example of anteroposterior montage, where you are having spikes and having maximum surface negativity at F8. The same thing, if you keep in the average montage, you can see nicely the maximum surface negativity occurring at F8, though there are spikes at FP2 as well as T4. So we can say this is possibly a temporal, it is coming from the right temporal lobe. The last part is the electrical safety of the machine, very important, because we do see some accidents happening in the EEG labs. So it is an important measure in defining the standards of electrical safety for biomedical equipment. And also, we should make sure that there is no leakage of current which can pass through the patient's body if the machine's own earthing connection is broken. So earthing is very important whenever an EEG lab is established. Also, whenever you is using extension cords should never be used along with the EEG machines. And whenever we are using the EEG machine in the ICUs, make sure that there is only one common ground for all the machines. And lastly, about the video EEG recording, which is nothing but the same standard EEG machine. In addition to that, you have a video which is focused on the patients continuously. And it consists of a video camera and an image mixer In addition, there should be mics as well as the speakers which should be present in addition to the rest of the EEG equipment which I have said. So this is an example of the video EEG equipment. And always most important in the video EEG is synchronization between the EEG and the video, that is the camera recording. The synchronization should be accomplished by calculating the video time from the EEG signal with recording time and the sampling frequency. And the video camera will have a lens. It should be mounted and there is a remote control which should be available to operate the camera. So the camera can have an infrared camera which can be used in the night times, or the camera is otherwise can record in the daytime. In the night time, when you switch off the lights also, we should be able to record the movements of the patient. And nowadays we do have autofocus cameras. Even if the patient moves, they automatically focus onto the patient and then do the recordings. So to summarize, the cortical pyramidal cells are the main source of EEG activity. The EEG potentials are generated by the summation of excitatory postsynaptic potentials and inhibitory postsynaptic potentials. The impedance of the EEG recording machine should be between 100 to 5,000 ohms. One should be knowing the common mode rejection ratio of the digital EEG machine, which should be more than 100 decibels. The sampling rate of the EEG machine should be at least twice the fastest frequency of the signal, that is 70 hertz. So it should be more than 140, but nowadays we get more than 210. The phenomena of aliasing occurs due to undersampling, so sampling rate should be good. And one should use common ground for all the machines whenever you are using EEG machine, along with other machines, especially in the ICU recordings. And I thank you for this opportunity, and to all the people who are hearing this, for your kind patience. Thank you.
Thank you,
Dr.
Sita.
Sita. And I see we are joined by Dr. Sangeeta. All of you will know Dr. Sangeeta Rawat is the Dean and a very dear colleague and senior epileptologist in Mumbai. And thanks, Sangeeta, for joining.
Sorry, I was a bit late for 10 minutes.
Sir, Professor Mehendee Ratta, you would want to say a few words, and then I'll check if there are any questions.
Yeah, there's one question for Dr. Sita, that what is the value of transverse montage? Though she has already shown that there is a high amplitude between O1 and O2. That's what she has shown. Dr. Sita, can you emphasize that again?
Yeah. The transverse montage is the one where you connect all the electrodes transversely. That is from the right to left transversely. In the longitudinal monitors, we connect them on the right side longitudinally and the left side longitudinally. So whenever we are looking at the phase reversals to identify where is the epileptogenic focus, we should get a phase reversal in both the montages at the same place. Then we are 100% sure that possibly that is the means irritative zone where we are recording the interictal epileptiform discharges.
I think this will be more clear in the talk on source localization by phase reversals. That is polarity talk. Yeah, so we'll be covering, maybe there will be some overlap. But generally, Dr. Sita, some machines which I see have only 2 montages and some have 7 or 8. So what do you recommend? I mean, ideally, one should see the discharge in as many montages as possible, so that we rule out artifact and see where the exact sources.
But means I really like the common average reference montage, though we use the longitudinal bipolar montage, transverse montage, and definitely circular montage for the end of chain phenomena, especially when you have spikes in the frontopolar or occipital regions. Whereas if it is in the central midline, possibly you need to use the transverse montage along with the longitudinal bipolar. If there is a parasagittal focus, usually common average reference helps. So always it's important to have all these in our, they are just programmable. You can keep them programmed and use as per the indication.
So
a very
Sita,
good talk, Sita.
Saying something.
Yeah, very nice talk. And I said, I mean, the fundas were very clearly cleared out, So I think excellent talk. I think there are lots of
Yeah, so there are
prairies
a
on
lot
the
of
question
questions on
answer.
montages, Sita. There's one question here. Ma'am, which montage is known as circumferential montage? So if you want to show the picture.
Circular montage is useful to identify the end of chain phenomena. Always which one should use, either for the frontal, if you are getting some maximum negativity FZ or F3, or at the O1 or O2, one should definitely use the circular montage.
So,
Next is, I think, will the recorded video be available at a later date? I think that Manjari
So-
only get that.
yes, we are recording the sessions, and with the permission of the speaker, we will edit the same to, remove extra portions in the beginning and the end. And sir, I think we should be able to upload the link to the website of Indian Epilepsy Society, sir.
Or we can send to all the participants who have participated.
Yeah.
So that's also possible, because so that they should get the maximum benefit.
So yeah, so there'll be some mechanism, because there will be one quiz at the end. So probably they want to revise it before the quiz.
Yeah,
So,
that's right.
yeah. I will again request all the participants to become members of the Indian Epilepsy Society. We reached up to 300 live attendees.
Yes.
I'd like to thank Professor Mehendi Ratta, Professor Sita J. Lakshmi, Professor Sangeeta Rawat. We have overshot the time by 15 minutes, but nevertheless, I'd conclude by thanking our sponsors, who are La Renon, who have given us the platform, as well as unrestricted educational grant in the form of a sponsorship to the Indian Epilepsy Society. And I'd welcome questions, and please join us sharp at 7 next time, the participants, because some of them were joining us a bit late. Sir and Sangeeta and Sita, any concluding remarks?
Manjari,
Yeah,
can
yeah.
I say a few words?
Yes, sir.
See, when faculty does a good job, it's the duty and responsibility of the dean to say thanks to the faculty that they have done a good job. Where is the
Yes,
dean?
yes,
The dean.
yes, sir.
Where
Yes,
is
sir.
the
I already told the Sita. she
And
did a
sir,
very good job.
Mehendra spoke on history of EEG.
Yeah, no. The dean has to thank the faculty that they have done a good job.
Thanks, Rita. I think you did wonderful job, and thank you, sir, and I think Manjari for detailing all the speakers and everything. I know being a dean, I'm contributing less time, but I'll really surely compensate in future once I'm out of deanship.
But we are very encouraged by such a strong response, which is
Yes,
not happening these
304. I
days,
think we
because
had
of
highest.
No, we have people from Nigeria, Bangladesh, they're all on.
Yes,
So-
we have
yeah.
participants from Indonesia, from Bangladesh, from Zimbabwe, from
Wow.
Nepal, from I think a few other countries I may have left off. I think Sri Lanka also. Yes.
Sri
Yeah,
Lanka,
304
Bangladesh,
we went to, I think.
Nepal, yeah. So I hope they will also join again and learn. But my one request to all the resident DM and DNB, that you must make note of these talks. Otherwise, you will
Yes.
forget.
Yes,
It cannot be
And-
retained
Or at
so
least
much in
read
the
this chapter immediately in your book within
Read and-
24 to 48 hours.
The speaker has done so much of hard work
Absolutely.
to give you the messages, and those you should write down in your diary, which should be preferably like your diary, which will be very helpful near the exam. So we are very encouraged with the response, and welcome all the delegates also from all over the world. And thank you so much for participating in large number. Don't hesitate to send the questions to Dr. Manjari, Dr. Sita, Dr. Sangeeta, or myself. We'll be happy to answer those. I think next time we'll try some way to give you our email, or maybe some number which doesn't disturb the speaker too much. So we'll try that.
Dr.
answer.
Abbasi is there. He's saying there's Pakistan as well. So I forgot Pakistan. I'm so sorry.
Yeah. Thank you so much for joining, Dr. Abbasi, and we
Iraq.
really appreciate. And there are friends from Nigeria, from Sri Lanka, from Nepal, and so many other countries. Yeah, it's and from Iraq also. Murtada Ali is from Iraq. So next time you can put your Dr. Ansam Hussain is also from Iraq, and Irfana is from Pakistan. So next time you can put your name so that we know each other. And from Nigeria, obviously, Solomon is also there. So thank you so much. And once again, we'll try to make it more practical, interactive, and like bedside, what you report EEG, then those sessions will also come. If required, sometime, Manjari, if I'm permitted, I prepared one 2-page requisition for EEG long back when I was in GB Park. So we'll be happy. It will take 5 minutes.
So we'll be having a session on reporting of EEG by Dr. Madhav Suri. So before that, sir, you can talk about what should be written in the form, because that's very important.
Yes.
Very often
Very
it's
important.
like just do EEG kind of.
Yeah.
We often forget to mention about medicine, state of the patient,
Yes, sir.
concomitant diseases, concomitant illness, and what Dr. Sita has said today. All that, even the technician is supposed to tick mark certain aspects. So I'll be happy to do that 5 minutes, Manjari, when we do reporting time. Yeah.
Yes.
Okay.
Yes.
So can we close the session?
Yes, sir, we'll close.
Thank
There
you,
are
sir.
some
Very
questions and we will cover them along the sessions. Thank you once again, Professor Mehendi Ratta, Dr. Sangeeta Rawat, Dr. Sita, and please do keep joining us, even though you may not be the speaker in that particular session. The next session is on 11th of Jan at 7 p.m. and it is covered by Dr. Samita Panda, who's head of Department of Neurology in AIIMS, Jodhpur. She'll be talking about normal EEG, basically alpha, beta, delta. Okay.
Manjari, somebody has asked, can people from outside India become members? Definitely.
So absolutely, people from outside India can become members. There will be an overseas membership. So yes, the answer is yes.
Please visit our website. It's very simple, www.epilepsyindia.org, and you will get all that information. Thank you so much.
Thank you. Good night. Happy New Year. Happy New Year to all.
Yeah.
Good night. Good night from India. It may be good afternoon or good morning in some countries.
Thank you, sir. Bye, Manjari. Thank you,
Thank
Sita.
you.
Thank you.
Bye.
Thank you.
Hello. Pramod? Pramod? Technical support?
Yes, ma'am. This is Mohi.
So we need the recording, and how will you send it to me? Because some of the participants want the recording for review at a later date. How will you send it to me?
Ma'am, I can download it and then I can share via link. One of the link I can upload it on Google Drive. Then
I will also need the participants' emails, because if we have to send it, we can also send it by email through Smash or something.
Yeah, ma'am.
So can you send it by tomorrow?
Yeah,
so that when they come for the next class, they have revised.
Yeah, ma'am. I will do, ma'am. Tomorrow I will give you.
Okay. Thank you.
Thank you.